Chapter 15, Linear Regression, from Learning Statistics with R, so it contains bivariate and multiple regression. The goal in this chapter is to introduce linear regression, the standard tool that statisticians rely on when analyzing the relationship between interval scale predictors and interval scale outcomes. Stripped to its bare essentials, linear regression models are basically a slightly fancier version of the Pearson correlation, section 5.7, though as we'll see, regression models are much more powerful tools. 15.1, what is a linear regression model? So we can see a scatter plot on the y-axis is my grumpiness from 0 to 100. And on the x-axis is my sleep from 5 to 9 hours. So you can see it's a negative correlation that's probably pretty strong, about 0.8. And then it shows the best fit regression line going on in. It's just slicing midway through the points, and then it shows not the best fitting regression line in which it doesn't follow the points. Since the basic ideas in regression are closely tied to correlation, we'll return to the parenthood.r data file that we were using to illustrate how correlations work. Recall that, in this data set, we were trying to find out why Dan is so very grumpy all the time, and our working hypothesis was that I'm not getting enough sleep. We drew some scatter plots to help us examine the relationship between the amount of sleep I get and my grumpiness the following day. The actual scatter plot that we draw is the one shown in figure 15.1, and as we saw previously, this corresponds to a correlation of r equals negative 0.90. But what we find ourselves secretly imagining is something that looks closer to figure 15.2. That is, we mentally draw a straight line through the middle of the data. In statistics, this line that we're drawing is called a regression line. Notice that, since we're not idiots, the regression line goes through the middle of the data. We don't find ourselves imagining anything like the rather silly plot shown in figure 15.3. This is not highly surprising. The line that I've drawn in figure 15.3 doesn't fit the data very well, so it doesn't make a lot of sense to propose it as a way of summarizing the data right. This is a very simple observation to make, but it turns out to be very powerful when we start trying to wrap just a little bit of maths around it. To do so, let's start with a refresher of some high school maths. The formula for a straight line is usually written like this: y equals mx plus b, or at least that's what it was when I went to high school all those years ago. The two variables are x and y, and we have two coefficients, m and b. The coefficient m represents the slope of the line, and the coefficient b represents the y-intercept of the line. Digging further back into our decaying memories of high school, sorry, for some of us high school was a long time ago, we remember that the intercept is interpreted as the value of y that you get when x equals 0. Similarly, a slope of m means that if you increase the x value by 1 unit, then the y value goes up by m units. A negative slope means that the y value would go down rather than up. Yes, it's all coming back to me now. Now that we've remembered that, it should come as no surprise to discover that we use the exact same formula to describe a regression line. If y is the outcome variable, the dv, the dependent variable, and x is the predictor variable, the iv, the independent variable, then the formula that describes our regression line is written like this: capital Y hat I equals B1 times capital XI plus B0. Looks like the same formula, but there are some extra frilly bits in this version. Let's make sure we understand them. Firstly, notice that I've written XI and YI rather than just plain old X and Y. This is because we want to remember that we're dealing with actual data. In this equation, xi is the value of the predictor variable for the ith observation, i.e. the number of hours of sleep that I got on day I of my little study, and yi is the corresponding value of the outcome variable, i.e. my grumpiness on that day. And although I haven't said so explicitly in the equation, what we're assuming is that this formula works for all observations in the dataset, i.e. for all I. Secondly, notice that I wrote y hat I and not yi. This is because we want to make the distinction between the actual data yi and the estimate y hat I. i.e. the prediction that our regression line is making. Thirdly, I changed the letters used to describe the coefficients from m and b to beta 1 and beta 0. That's just the way that statisticians like to refer to the coefficients in a regression model. I've no idea why they chose beta, but that's what they did. In any case, beta 0 always refers to the intercept term, and beta 1 refers to the slope. Excellent, excellent. Next, I can't help but notice that, regardless of whether we're talking about the good regression line or the bad one, the data don't fall perfectly on the line. Or, to say it another way, the data yi are not identical to the predictions of the regression model y hat I. Since statisticians love to attach letters, names, and numbers to everything, let's refer to the difference between the model prediction and that actual data point as a residual, and we'll refer to it as capital E to the I. Written using mathematics, the residuals are defined as e to the I equals yi minus y hat I, which in turn means that we can write down the complete linear regression model as y to the I equals beta 1 times xi plus beta 0 plus capital E to the I. 15.2, estimating a linear regression model. Okay, so they're showing, it looks like a plot of the residuals. On the y-axis is, again, my grumpiness from 0 to 100, and again on the x-axis is my sleep in hours from 5 to 9. And now we can see the regression line, the data points, and then we can see the vertical distance between each data point and the regression line drawn in. Okay, and then it's showing a similar graph with the regression line distant from the data. Okay, so you can see because of the slope, some of the data points have a really big vertical distance between themselves and the line. Okay, now let's redraw our pictures, but this time I'll add some lines to show the size of the residual for all observations. When the regression line is good, our residuals, the lengths of the solid black lines, all look pretty small as shown in figure 15.4, but when the regression line is a bad one, the residuals are a lot larger, as you can see from looking at figure 15.5. Maybe what we want in a regression model is smaller residuals. Yes, that does seem to make sense. In fact, I think I'll go so far as to say that the best fitting regression line is the one that has the smallest residuals, or better yet, since statisticians seem to like to take squares of everything, why not say that? The estimated regression coefficients, beta hat 0 and beta hat 1, are those that minimize the sum of the squared residuals, which we could either write as the sum of I, bracket, y to the I minus y hat to the I, end bracket, squared, or as the sum of I, capital E to the I squared. Yes, that sounds even better, and since I've indented it like that, it probably means that this is the right answer, and since this is the right answer, it's probably worth making a note of the fact that our regression coefficients are estimates. We're trying to guess the parameters that describe a population, which is why I've added the little hats, so that we get beta hat 0 and beta hat 1 rather than beta 0 and beta 1. Finally, I should also note that, since there's actually more than one way to estimate a regression model, the more technical name for this estimation process is ordinary least squares regression, OLS regression. At this point, we now have a concrete definition for what counts as our best choice of regression coefficients, beta hat 0 and beta hat 1. The natural question to ask next is, if our optimal regression coefficients are those that minimize the sum squared residuals, how do we find these wonderful numbers? The actual answer to this question is complicated, and it doesn't help you understand the logic of regression. As a result, this time I'm going to let you off the hook. Instead of showing you how to do it the long and tedious way first, and then revealing the wonderful shortcut that R provides you with, let's cut straight to the chase and use the LM function, short for linear model, to do all the heavy lifting. 15.2.1, using the LM function. The LM function is a fairly complicated one. If you type $LM, the help files will reveal that there are a lot of arguments that you can specify, and most of them won't make a lot of sense to you. At this stage, however, there's really only 2 of them that you care about, and as it turns out, you've seen them before. Formula. A formula that specifies the regression model. For the simple linear regression models that we've talked about so far, in which you have a single predictor variable as well as an intercept term, this formula is of the form outcome squiggly predictor. However, more complicated formulas are allowed, and we'll discuss them later. Data. The data frame containing the variables. As we saw with the AOV function in Chapter 14, the output of the LM function is a fairly complicated object with quite a lot of technical information buried under the hood. Because this technical information is used by other functions, it's generally a good idea to create a variable that stores the results of your regression. With this in mind, to run my linear regression, the command I want to use is this: regression.1 equals LM bracket. Formula equals dan.grump squiggly dan.sleep, comma, data equals parenthood, end bracket. Note that I used dan.grump squiggly dan.sleep as the formula. In the model that I'm trying to estimate, dan.grump is the outcome variable and dan.sleep is the predictor variable. It's always a good idea to remember which one is which. Anyway, what this does is create an LM object, i.e. a variable whose class is LM, called regression.1. Let's have a look at what happens when we print function it out. Print bracket regression.1 end bracket. The output is call LM bracket formula equals dan.grump squiggly dan.sleep, comma, data equals parenthood end bracket. Coefficients. The intercept is 125.956 and dan.sleep is negative 8.937.